So find the Maclaurin series representation of f of x equals to 1 plus x to the power of k, where k equals any real number, where k equals any real number. Okay, this one's going to be hard because we have two different variables that we have to keep track of. Okay, so Maclaurin series representation, always the same, start the same way. We know that if it exists, then it must be true that this, our function, is going to be equal to some series that looks like this. And we're going to need to look at the nth derivatives evaluated at 0 divided by n factorial times x to the power of n. Okay, so we got to start taking derivatives of this guy, and hopefully that's not too bad. So we start off with our original function, f of x equals to 1 plus x to the power of k, and then the first derivative, of x is equal to bringing down that k, right? Let's think of it as some constant. Once we've chosen it, x can be any real number, but then we choose it to be some constant value, and at that point, with respect to x, it's just some constant. Right? Think of it like 7, for example. Bring it down in front, and then we subtract 1 from the exponent, right? It becomes 1 plus x to the power of k minus 1. And then, good old chain rule, we got to take the derivative of the inside part times the derivative with respect to x of 1 plus x. Luckily, this is getting hard enough, luckily for us, that's just going to be 1. The derivative of this part is just going to be 1. So this is our first derivative. Okay, so since that's just 1, let's just erase it. It's going to get really messy. We don't need extra stuff on here. That's just a 1. Okay, so now let's take the next derivative. So we work our way down, and now the next derivative is going to be the second derivative of our function. Right, so that's just some value k, and then we bring down the exponent. That'll be a k minus 1 times 1 plus x to the power of k minus 2. Good. And then again, there's this derivative with respect to the inside part, 1 plus x. And again, that's just going to be 1. So we don't need it. Let's get rid of it. It's going to be messy enough without that. But it's implied that there's a times 1 in there. Okay, so let's do a couple more. The third derivative with respect to x is going to be equal to k times the k minus 1 times a k minus 2. Right, bringing that exponent out in front as a factor, times the 1 plus x to the power of k minus 3. And then the next derivative, the fourth power x, is equal to k minus 1, k minus 2, k minus 3, and 1 plus x to the power of k minus 4. Okay, let's do one more. F to the power of 5. So this is the fifth derivative, shouldn't say the power of. The fifth derivative of our function, x, okay, that's going to be equal to k times k minus 1, k minus 2, k minus 3, k minus 4, the power of, right, there's a, oops, why did I change my mind? So 1 plus x, the power of k minus 5. Okay, so then we keep going. Hopefully there's enough there to establish a pattern. And then for each one of these, we want to evaluate f of 0. So I'll have f of 0, that first one is going to be equal to 1 plus 0 to the power of k. 0, 0. And now 1 plus 0 to the power of k, well, that's just going to be 1 to the power of k. 1 raised to any number is just going to be 1. Okay, then let's work with the next one then. Then the next one is going to be the first derivative, evaluated at 0. And this one is going to be k times 1 plus 0 to the power of k minus 1. We're going to evaluate this at 0, so put a 0 there, put a 0 there. Replace the x's, right? There's a lot of variables running around. Don't confuse yourself. This is a function of x, right? Once the k is chosen, you can just think of it as a constant. Okay, so then this is going to result in k times 1 to the power of k minus 1, and that's just going to be equal to 1, so the next one equals to k, right? So we have that the first one is a 1, the next one is a k. Okay, so now going on to the second derivative, evaluated at 0, well, that's going to be k, and then the k minus 1, and then we have a term of 1 plus blank to the k minus 2. Okay, and if we replace all these values with a 0, okay, well, we start to see what happens. This is going to be a k times a k minus 1, and then this is going to turn out to be 1 to the power of something, which is 1. So this is our result, k times k minus 1. And I think we have enough established to start skipping a little bit of work here and start seeing what the pattern, and then we start to see what the pattern is going to be. So if we skip on over to the third derivative, evaluated at 0, I can see that this part is going to go away, right? All the terms that have a 1 plus 0, the power of something, are just going to become 1. So this one is just going to end up being the part in front involving the k, right? All the factors that involve a k. So this one's going to be k times k minus 1 times k minus 2. And then the next one, the fourth derivative evaluated at 0, that's going to be k times k minus 1 times k minus 2 times k minus 3, right? And that's evaluated at 0. Last one here, this is going to be f of the fifth derivative evaluated at 0. Again, that means that all these terms survive, and then we end up with a 1 to the power of something. So this one's going to be k times k minus 1 times k minus 2 times k minus 3 times k minus 4. Right, I know to stop at 4 from that. Okay, and this is when we're evaluating at 0. Okay, so we want to jump to a pattern, and the pattern is not easy at all. So what's going to happen as we go down the line, dot, 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 what's going to happen at n? As we take the nth derivative of x, what's going to happen? All right, well, I can see that they all start off with k, and they start off this countdown. K, k minus 1, k minus 2, dot, 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 right? And where does it stop? Well, it stops there. How does this relate to 5, right? That's what I want to know. See, this stops at k minus 3, and then we're talking about the fourth derivative. The fourth derivative stops off at k minus 3. The fifth derivative stops off at k minus 4. So is it clear that from here to here, this is 4 minus 1? That's good. That gives me that 3. Well, excuse me. Is it clear that if I replace, well, if I replace this term with something that involved a 4, I would want to do something like this, k minus 4, that way it involves that guy, but it wouldn't be equal to this. So I would be off by a little something. I could add a 1. Good. You see how k minus 4 plus 1 is the same thing as k minus 3. And then same thing over here, if I want to involve the 5, right? I'm making it more complicated than it needs to be because I want to involve this 5. That's what I want to do. I want to involve the 5. And so how do I represent this involving a 5? I want to say it's k minus 5. But then it wouldn't be equal to this since this is k minus 4, not k minus 5. So again, I add a 1. I add a 1, it gets me to that one. And that's how I know where to stop. So now that I have that pattern going, then I know that this guy is going to continue, dot, 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 dot. And where does it stop? It's going to stop at k minus n plus 1. Right? That way I involved this guy, the nth derivative. It's going to be k minus the nth derivative plus 1. Right? It worked from all the other ones that came before it. Right? It also works for this one. If I want to involve this 3 and show, figure out the place where it stops, it's going to be a k minus 3, and then I put a plus 1, and then that gets me to what I want. Right? So the pattern is established. It's a hard pattern to notice. So hopefully it's clear that that's how I figure out where to stop. Okay. And then I still have this term of 1 plus x to the power of k minus n. So now it is k minus n. This one, the exponent is equal to k minus n, where n is the derivative. Good. Okay, so now if I evaluate this guy at 0, it's going to get rid of that, so it's just going to give me this. So f of n evaluated at 0 is going to be k times k minus 1 times k minus 2 dot, 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 dot. And where do we stop? We stop at k minus n plus 1. Good. And that's when we evaluate it at 0, just following along with this pattern that we have over here. Okay, so now we have the value for the nth derivative evaluated at 0, so we can come back up here to this and replace this part with what we just found. Okay, so let me rewrite it over here. So we have that 1 plus x to the power of k is equal to the sum as n goes from 0 to infinity of, and then we have this k minus 1, k minus 2, dot, 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 and we stop at k minus n plus 1 all over n factorial x to the n. N factorial x to the n. Okay. So when is this going to converge? Right. That's the question. When is this going to converge? So let's apply. Okay, so let's apply the ratio test on this guy. Ratio test. So we want the limit as n goes to infinity of the absolute value of, and then we have this in the denominator, so that'll be k, and then k minus 1, and then k minus 2, dot, 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 and then we stop at that k minus n plus 1. And then there's a n factorial in the denominator, x to the nth power, right? So all of that is just my a sub n. That's just a sub n. I still have to think about the n plus 1 case up here. Okay, so there's this other fraction up in the numerator. That'll be the n plus 1 factorial case. And then there's an x to the n plus 1 term up there. And then there's this countdown. And where does the countdown stop? Well, we got to go up to including an n plus 1 there. So if we start off at k, and then we have a k minus 1, and then a k minus 2, dot, 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 dot. Then the next one is going to be k minus n plus 1. And the one after that is the one that includes an extra term of n plus 1. So the one that goes right in here, put it over here, the one that goes right in there is going to be k minus plus 1, and then it has an n plus 1 in here. Right? So it used to be n, right? But we want to go one more term. It's the n plus 1 term. And when we do that, well, we have to distribute this minus. So we'll end up with k minus n minus 1 plus 1. And now these two cancel. This cancels with that. And so we'll be left with just the k minus n value. And that's what goes right in here. So this little sequence of products here stops at k minus n. Ugly. Okay, so hopefully that made sense. Let's get rid of this guy. And all of this is still inside this giant absolute value. There's this one giant fraction here. And so this is the a sub n plus 1 is the a sub n. So we can begin to try and simplify this a little bit. This is going to be the limit as n goes to infinity of the numerator. So I'm not going to do anything to simplify that right now. I'm just going to break this down into two pieces and then break that down. Those look familiar. So we have k minus 1, k minus 2, dot, 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 dot. There's this k minus n plus 1, and then there's this term of k minus n. And then we're going to multiply that by x to the power of n times x to the power of 1. That takes care of this line. Below that, we're going to have just n plus 1 times n factorial times the reciprocal of the denominator, which will end up giving me an n factorial divided by k minus 1, k minus 2, k minus 3, well, actually, let me do that. K minus 2, dot, 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 and this one ended at the k minus n plus 1. K minus n plus 1. And then there's also this x to the power of n term there. Okay, all in a giant absolute value. Okay, so now we can cancel some stuff. This reduces with that. And then this reduces with this. And then on a term by term, right, the k cancels with this k. And the k minus 1 cancels with this k minus 1. And then k minus 2. And then k minus 2. Dot, 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 dot. So they will all cancel up to there. So this is the only one that survives all that cancellation. And a factor of x in the numerator as well. And in the denominator, the only thing that survives is this one. So let's recopy all of that. This is going to then be equal to the limit as n goes to infinity of, and I'll just leave in the absolute values for now. The only thing that survived with the numerator is going to be k minus n times an x, and then divided by an n plus 1. That's it. just an n plus 1, right? That's the only one that survived there. All of those guys got canceled. Good. Inside the absolute values. Okay, so what can we pull out? Well, we don't know what x is. X could be any number, so we can't pull it out of the absolute value. N plus 1 can be removed, but we don't know what this is either. K minus n. I don't know. Is a k a large number? Depends on the value of n, and I don't know if this is positive or negative, so let's leave it in there. This is the limit as n goes to infinity of 1 of k minus n in absolute values all over n plus 1 times the absolute value of x. Okay, well, we can apply our usual tricks, keeping in mind that n is counting numbers, 1, 2, 3, 4, 5. So this is definitely going to be some positive number. Depending on the value of n, it might be small, but it's still going to be positive. So this is another version of 1 we can distribute, and we can bring this inside here because it's positive. It doesn't have any impact. Right? So if you want, we can also just do this. Either way. Okay, so now that means that we can tuck that in there, and we do the limit as n goes to infinity of the absolute value of k over n minus n over n, which is 1 in absolute values, divided by 1 plus 1 over n. Good. Okay, so n times the absolute value of x. The limit as n goes to infinity, right? As n goes to infinity, this is getting infinitely small. Once we've chosen a value for k, right? For a selected value of k stays still, as stationary, it's a constant, then this denominator is going to grow infinitely large. So this part is going to grow towards 0. And as n goes to infinity, this part will grow towards 0. So we'll end up getting, as n goes to infinity, we'll end up getting something that's approaching 0 minus 1. So it's approaching negative 1. And the absolute value of negative 1 is going to be 1. So this whole thing is approaching 1. The denominators are also approaching 1. So the limit as n goes to infinity of this entire thing is just going to be equal to 1 times the absolute value of x. That's what we get out of this. And remember, we're doing the ratio test. So the ratio test that this is going to converge as long as this is less than 1. Right? So we get that the radius of convergence r equals 1, and the interval of convergence is going to be negative 1 less than x less than 1. Okay? All right, well, we'd have to test the endpoints, and also we have to keep in mind the value of k. Bring it all together and see what we get. So we found that, let's go back over here. We found that this was true. So let me just copy that again. We've established that 1 plus x to the power of k is equal to n goes from 0 to infinity of, and then we have this countdown that starts to happen. K minus 1, k minus 2, dot, 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 and then it stops at k minus n plus 1. So it stops. The whole thing gets divided by n factorial, and then there's an x to the nth term. Okay. This is so popular, so famous, that we give it its own notation. This is exactly the same thing as this notation, kn, like this. Right? So this means that. So a very popular way to represent this is that 1 plus x to the power of k is equal to the sum as n goes from 0 to infinity of k, choose n, x to the nth power. Good. And now when is this going to work? When is it going to converge? Well, we partially showed some of the answer, but not entirely. And we're not going to spend that much more time on it because it is kind of confusing. So this is true, right? This will hold. This equation is valid in one of two ways, or in a couple of cases here. So if k is a positive integer, a positive integer, that means that k equals to 1 or 2 or 3 or 4, dot, 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 then this is true. It will converge. Then 1 plus x to the power of k equals to 0 to infinity of k choose n, x to the n, for all real values of x. Right? So x being any member from negative infinity to positive infinity will be true, as long as k is some positive constant. Okay? So, for example, what if k was equal to 3? So we're saying that if k is equal to 3, then we have the case of 1 plus x to the power of 3. And so this will be equal to this. 3 choose n as x to the power of n. Okay, and this will be true for any value of x, right? So this will hold. That's what that means. Okay, well, on the other hand, what if k is not a positive integer? There's another couple of ways in which this could work out. So, on the other hand, if k is greater than, if k is greater than -1 but less than 0, k is greater than -1 but less than 0, then our statement will be true. Then 1 plus x to the power of k will be equal to the sum as n goes from 0 to infinity of k choose n, x to the n. And this will be true for values of x that are between -1 and 1. This is valid, or will converge. For x being a member of the interval between -1 and 1, inclusive of the 1. So x will be allowed to be 1, but it's not allowed to be -1, right? So that's for k being one of these values. So for example, if k equals to -1/2, if k equals to -1/2, it lands in this zone in here, right? Which means that 1 plus x to the power of -1/2 is going to be equal to this, 0, and then we have our k n x to the n. It's going to be equal to that, but only if this is true. Only for x being a member of an element of this set, -1 to 1, inclusive of the 1, not inclusive of the -1. Okay. So to further punch this in, if k equals to -1/2 and x equals to +1/3, then 1 plus 1/3 raised to the power of -1/2 is going to be the same thing as the limit as this goes from 0 to infinity of k is equal to oh, sorry, made a mistake here. This is 1/2. Right, so this is 1/2. So this is going to be negative 1/2 in there. It goes from negative 1/2, 1/2. Okay, so this will go from negative 1/2 n to positive 1/3 to the power of n. Right, so here the x is a value inside this interval, and the k is a value inside the interval from negative, in here, from negative 1 to 0. So it's going to be a valid statement. Right, so it'll be true that this Taylor series representation is going to be equal to exactly this. Okay, so the other case we're going to think about is if k is just some positive value greater than or equal to 0, then in this case, then the 1 plus x to the power of k is going to be equal to this representation, this Taylor representation, Ch11 of x to the nth power, and this is going to be valid for x being a member of, an element of, the set from negative 1 to 1. So these two are almost identical, the only difference being that here we want to include this negative 1, right? We put a bracket there, we include the negative 1, and in this case we don't include the negative 1. That's all. So there's one extra little case where this is valid. So for example, if k was equal to positive 1/3, right? It'd be positive. It's not a counting number, right? If it was a counting number, it would fall under this kind of criteria, this condition over here. But it is positive, so therefore this will be true, and it will allow x to be any number between negative 1 and 1, inclusive of the endpoints, right? So if k equals to 1/3 and say x equals to 1/5, then we're following these guidelines. It's a positive value for k. It's not a counting number like that one, and x is a value inside this zone. So this lets me know that this will be true. 1 plus 1/5, 1 plus 1/5 raised to the power of 1/3 will in fact be equal to the sum as n goes from 0 to infinity of the k, which is equal to 1/3, choose n, and then the x raised to the power of n. Raised to the power of n. Now, what exactly that means, we will explore that in a little bit, but that's what this is saying. So as long as the k meets that condition, then the x meets this condition, that means that this is going to hold true. It will converge. This will be a valid Taylor representation of that guy. If it's not in that range, if it fails one or the other, then all bets are off. It's not necessarily going to be true, right? So in other words, just to kind of go in the opposite direction, for example, if k was equal to 1/3, but x was equal to 7, right? 7 is not in this zone. So it would no longer be true that 1 plus 7 raised to the power of 1/3, this would no longer be equal to this, to infinity of 1/3 choose n, and then 7 raised to the power of n, right? It fails to be true, right? Because this is a case where the k is a positive number. This would be a case where the positive k is equal to some positive number. It's not an integer though. If it was an integer, we'd fall back over here to this situation. If k had been one of these integers, then it would be true. But k is a positive value, and the x value is somewhere outside of this zone. Therefore, this is no longer true. Right? So it's kind of a complicated set of conditions. Okay, let's try one where we actually work it out. Okay, so now the last case to think about is what if k was less than or equal to -1, right? We've covered everything else. We talked about what happens when k is a positive counting number, 1, 2, 3, 4, 5. Okay, that means that this is valid for all real numbers. And we covered the case when k is a number strictly between -1 and 0. Okay, in that case, then this is when it converges. We covered the case when k is some value that's positive, not necessarily the integer values, but positive. Then we know for sure it'll converge on this set, including the endpoints. And now, what if k is strictly less than or equal to -1? Well, then in that case, then this is true. Goes from 0 and goes from 0 to infinity of kn x to the nth power. And this is going to be true for x being a member of -1 to 1. Okay, so no endpoints. So if k is some negative value that's strictly less than or equal to -1, it's valid just in this set. If k is a real number greater than 0, not necessarily a counting number, then it's valid in this set. And then if k is between -1 and 0, it's valid in this set. And if k is some integer value, 1, 2, 3, 4, 5, then it's valid in this set. Okay, well, we can simplify this a little bit by noting that all 4 of these sets include this one, right? This one, -1 to 1, not inclusive of the endpoints, is a proper subset of this one. -1 to 1 is in here, right? It's just strip away the endpoints and we get this one. And then -1 to 1 is also a proper subset of this one. Just strip away this endpoint. And finally, -1 to 1 is a proper subset of this one as well. So a way to simplify this crazy complicated thing is just to restrict yourself to letting x equal to this, right? If we let x be a value between -1 and 1 without thinking about the endpoints and without going outside of that, then we can just kind of simplify the situation and say that k could be anything, right? It could be a positive number that's not a counting number. It could be a positive counting number. It could be a decimal between -1 and 0. It could be a value that's less than -1. In all 4 of these cases, as long as x is inside the subset, then everything works well. Okay? All right, so we can condense all of that into the statement that's in our book. Let's look at that guy. Okay, here it is. So this is called the binomial series. If k is any real number, positive, negative, decimals, counting number, anything at all, and x, the absolute value of x, is less than 1, that means that x is in the interval between -1 and 1, then it's true that 1 plus x, the power of k, is equal to exactly this, just like we had gotten it. Okay, so let's move on to another example. All right, let's try one more problem. So since we just finished working with a binomial, let's work out number 42. So number 42, use the Maclaurin series in table 1 to obtain the Maclaurin series for the given functions. Okay, so we'll look at table 1 in a second, but This is basically asking us to refer back to the binomial equation we just came up with, right? So we're gonna use this guy we just derived. We're going to use the binomial series, the one we just derived, to be able to answer that one. Okay, so let's get started. Okay, so first of all, we want to try and manipulate this a little bit. I want to manipulate it because I want it to somehow get to a point where we get to use that 1 plus x raised to the power of k is equal to the Taylor series expansion of k choose n x to the nth power, right? So we want to get to use this, so I want to manipulate this in a way that gives me that in, and be able to plug that in. So I'm going to first of all separate the product here. So this will become x squared times 1 over the square root of 2 plus x. So we're getting a little closer, but I need this to be a 1, not a 2. It's a subtle difference, but it's important. We need that to be a 1. So I'm going to factor out a 2 from inside there, and it'll then be equal to this. This will be x squared times 1 over, and then I'll factor out a 2, so I'll have a 1 plus x over 2, right? Meaning if I distribute this 2, I'll get a 2 plus x over 2. And then x there. And now all of that is still inside this root, so we haven't gotten rid of it yet. Okay, so now I can separate this into x squared times 1 over root 2 times 1 over root 1 plus x over 2. Good. And so now this, I can keep that together on the side, x squared and then root 2 times, and then this, I can rewrite it as 1 plus x over 2 raised to the power of negative 1/2. Okay, so now we've hit pay dirt, right? So now it looks like something like that. So now I can make that proper exchange. This is going to be equal to x squared over root 2 times this part, which is the sum as n goes from 0 to infinity of the k. The k in this case is equal to, so for us, this is equal to that, where the k is equal to negative 1/2, and the x is actually x over 2. So for us, x over 2 is this part. That part there is the x over 2. And the k here, this part, is the negative 1/2. So when we plug it into this guy, we'll end up with k, which is equal to negative 1/2, choose n, and then we have our term, which is equal to x over 2 raised to the nth power. Right, and then we multiply those, and this will be valid for this thing, right? This is valid for the absolute value of x is strictly less than 1. That's the binomial series looks like this. For us, that'll be this whole thing. This is valid for the absolute value of x over 2 being less than 1, which means that the absolute value of x must be less than 2, which means that x must be a value between negative 2 and positive 2. As long as x remains within that domain, then this will be true, right? We've stated that this, let's bring it all the way down, right? Leave this alone. So this equals that, equals that, equals that, equals that, and it equals this. Okay, but we can do better than that. Let's expand this and simplify it and do what we can with it. So what does this mean? This means that, let's leave this alone, we have this over that. And now let's start expanding this. So this is going to be equal to negative 1/2, choose 0. Negative 1/2, choose 0. And then it's going to be x over 2 raised to the 0 power. That's what happens when n equals to 0. Plus, and then we have negative 1/2, choose 1. And then we have x over 2 raised to the 1 power. Plus, then we have negative 1/2, choose 2. And then x over 2 raised to the 2nd power. Plus, negative 1/2, choose 3. X to the 3rd power. Let's do one more. And then we have negative 1/2, choose 4. X to the 4th power. Okay, dot, 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 dot. Hopefully that's enough to establish a pattern. Okay, so we're going to adopt the notion that this is just going to be a 1. Okay, so any number choose 0 is going to be a 1, and then any value raised to the 0 power is 1. So that term is just going to be a 1. Plus, and now this guy, we end up with a negative 1/2 over 1 factorial, right? Remember the definition of what it means to have this. So remember that, let's put it off on the side here, that k choose n means that we have k times k minus 1 times k minus 2, dot, 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 dot. And we stop at k minus n plus 1, and all of that gets divided by n factorial. Right? So using that little formula for this, where n is a 1, so we're only going to do one term, so that's going to be the k. And then we end up with an x over 2 to the power of 1. Right? So this is the case where n equals to 1. If n equals to 1, then minus 1 plus 1 is 0, and so it's just k. Right? So it's that first term. That's why this is just k. Right? This is k minus n, which in this case is a 1, plus 1. Well, then that just becomes k, which is the kth value, which is just going to be equal to negative 1/2. Okay, I think the pattern is a little easier to see as we move on. Let's move on. Okay, the next one is going to be 2 terms. We're going to end up having a negative 1/2, and then it's going to be negative 1/2 minus 1. Right? This is the kth one, and then this is the k minus 1 term. Right? And this is where n equals to 2. Right? So if we replace this with a 2, right, if we replace that guy with a 2, we end up with k minus 2 plus 1. That's k minus 1. And that's how we know when to stop. We stop at k minus 1. Okay, moving on. Then we need to divide this by 2 factorial. And then we have a term of x over 2 raised to the power of 2 plus, okay, so again, where do we stop? I know it's this countdown of negative 1/2, and then we start counting down. We have n equals to 3, so if we put a 3 into here, a 3, we would end up with k minus 3 plus 1, which is k minus 2. Right? So we need the kth term, we need the k minus 1, and we need the k minus 2 term. That's how we know when to stop with this pattern. Right? That's what this is saying. Okay, so then k is negative 1/2. So the next term is going to be negative 1/2 minus 1 times negative 1/2 minus 2. And that's how we know when to stop, at a minus 2. Okay, this all has a 3 factorial, and then that whole thing is being multiplied by x over 2 raised to the power of 3. I know, this is ugly. One more, last one. Plus, okay, this is going to be k. This is going to be the 1/2, which is the k. And there were 3 terms, so we know we had to go to 4 terms. That's going to be negative 1/2 minus 1, negative 1/2 minus 2, and negative 1/2 minus 3. 1, 2, 3, 4 terms divided by 4 factorial times this x over 2 to the power of 4 plus dot, 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 dot. Okay, so there's that pattern. Ugly little pattern, but we can try and make it a little bit nicer. Okay, so here's the whole thing. Okay, so let's try and simplify this as best we can. So first of all of these fractions that have minus 1/2 minus 1, minus 1/2 minus 2, let's simplify those a little bit. So this is going to be x squared over root 2. Leave that alone out there. There's a 1 there. Just for the sake of making this larger, I'm going to separate the numerator and the denominator. So I'm going to say that this is plus, this is negative 1/2 times 1 over 1 factorial. And then I'm going to separate this as well and say that that's just 1 over 2 x to the first. Right, so I'm just kind of expanding out this whole thing there. Plus the next one. So again, I have the fractions, and the fractions are going to be negative 1/2 times, and then this fraction is negative 1/2 minus 1. That's going to be negative 3 over 2. That takes care of these two. There's still a 1 over 2 factorial. That takes care of that. And then separating this, there's a 1 over 2 squared times an x squared term. That takes care of everything here. Good. Plus, right, very messy. Maybe I should make my pluses with a different color to really pop out because it's getting really messy. So this is this plus, this is this plus. That takes care of that one. And then this whole thing is that. So there's a plus sign there, and now there's a plus sign here. So this whole thing comes from there. And then this whole thing is this, expand it all out. Right? I want to expand it all out, see if we can see a pattern. Now I'm going to expand this one out. Okay, so again, there's these fractions, and there's a negative 1/2 to begin with, and then we subtract 1 from it, which gets us to negative 3 over 2. And then we subtract 1 again, which gets us to minus 5 over 2. That takes care of my 3 fractions. And then there's a times 1 over 3 factorial. And then I'm going to separate this as well, which takes me to 1 over 2 to the power of 3 times x to the 3 power. Okay, that takes care of all of those terms in there. Plus, last one, ugly, but last one. Let's expand this whole thing out. And so once again, I have the numerators. That's going to be negative 1/2 times, and then we subtract 1. That gets me to negative 3 over 2. Subtract 2. That's going to get me to negative 5 over 2. Subtract another 2. That's going to get me to negative 7. Negative 7 over 2. That takes care of all those fractions, right? 1, 2, 3, 4 fractions, 1, 2, 3, 4 fractions. And then I have this times 1 over 4 factorial. That takes care of this. And then this guy, again, I'm going to separate it. And I'll have a 1 over 2 to the power of 4, x to the power of 4. And that takes care of that term right there. And then plus dot, 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 dot. Hopefully we have enough now to start to see what the pattern is going to be. Okay, as ugly as it is, hopefully we start to see a pattern. So let's combine all these powers of 2. There's a lot of 2's running around. 2, 2, 2, and then there's some 2's there. We see some of these factorials, right? So hopefully those patterns also kind of pop out. And then, well, the first thing I want to note is the signs. So let's see. Let's begin simplifying this a little more and see if the pattern starts to come out. Leave the 1 there. And let's just pay attention to the signs. This term is going to be negative, right? Because there's only one sign. There it is, and it's negative. So I know this one's going to be a minus. Okay, and then here I have a minus times a minus. So I know that this term is going to be plus. So it's going to turn into a plus sign. And then the next one, I know I have a negative times a negative times a negative. That's 3 of them. I know it's going to be a minus. This is going to be a case where we have an alternating positive, negative, or plus, minus, plus, minus, plus, minus. So I can see that pattern exists here, right? This last one is going to be 1, 2, 3, 4 of them. They're all negative. So they multiply to give me a positive one. Okay, so now going back to the powers, we have powers of x. That's an easy pattern to notice as well. X to the first, x to the second, x to the third, x to the fourth. Okay, so then I'm going to squeeze it into here. This is going to be an x to the first, and x to the second, and x to the third, and x to the fourth. Right, that takes care of that guy. The factorials are also pretty easy. There's something to do with a factorial in the denominator. 1 factorial, 2 factorial, 3 factorial, 4 factorial. So there's going to be a fraction in front of here for all of these guys. So a giant fraction, a giant fraction, a giant fraction. And the denominator here has a 1 factorial. This one has a 2 factorial. This one has a 3 factorial. This one has a 4 factorial. Right? So I've accounted for all of those. Now there's all these 2's running around, so let's see what's happening with the 2's. I'm going to start backwards. There are 4 powers of 2 here. 4, 5, 6, 1, 2, 3, 4, and 4. I should say. So that gives me 8. This is 2 to the power of 8. Right? There's 4 there. 5, 6, 7, 8 of them. Okay, in this term, there's 3 there, 3 factors of 2, 3, 4, 5, 6, 2 to the 6th power. And then here, there's 2, and then 3, 4. This is 2 to the 4th power. And then over here, well, there was just 2 of them, 2 to the 2nd power. Okay, so a nice pattern starts to emerge with all those 2's everywhere. Okay, and now the only thing that is missing is these extra numbers up top here that we got as a result of multiplying all these fractions, right? All these fractions have a common denominator of 2. That's how we got all these 2's running around everywhere. But now they also create this pattern where this first one is going to be just a 1, right? Because we have, okay, we already took care of the minus. So it's 1, 1, 1. It's just a 1. And then we have a 1 and a 3. A 1 times a 3. And then we have a 1, a 3, and a 5. A 1 times a 3 times a 5. And then we have a 1, 3, 5, 7. Okay, so we start to see a pattern. 1, 3, 5, 7. Good. So based on the pattern that we've established here, I think it makes it pretty easy to guess what the next term is going to look like, right? If you can guess what the next one's going to look like, then you already have a pretty good idea of what the pattern is, right? So the next pattern, okay, we have positive, minus, plus, minus, plus. So I know this next one's going to be a minus. And I know that this next one is going to be x to the power of 5. And I know that this is going to be a 5 factorial. And it's going to have a x to the power of 5. And look at the powers of 2. 2 to the 2nd, 2 to the 4, 2 to the 6, 2 to the 8. what's the connection, right? We got to think about what's the connection between the power, here's the 4, and then this goes 2 to the 8. Here the power is 3, and this goes 2 to the 6. Here the power is 2, and this goes 2 to the 4th. So is it clear that the connection between this and this is that it doubles it? This doubled gives you this one. This one doubled gives you that one. So with that pattern in mind, it should be clear that this one should be 2 to the power of 10. Should be 10 multiples of 2 because it's doubling that one. Good. And then all that's missing is this multiplication, and it looks like it's going to be a bunch of odd numbers. The 1, the 3, the 5, the 7, and now the 9. Good. And how do we know when to stop? Okay, what's the pattern again with that? Notice that this stops at the first odd number that is 1 less than double that one. Right? I noticed that because this is an 8 and that's a 7, and it stopped 1 below that. This is a 6, and that one was a 5, so it's 1 below that. 10, and that's 9, that's 1 below that. And we said that this was doubling it. So double this number and subtract 1, and that's how you're going to figure out which odd number you need to stop in. Okay, so now that we have the first few terms here, let's extract this out. Let's say if we keep going out to infinity, what would happen? So let's see, the next term would be x to the 6th, and the one after that will be x to the 7th. So let's say that it kind of wrapped around and like dot, 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 dot. What happens at the nth one, right? So we'll go out to the nth one, and let's see if the pattern holds, or if we can see what our pattern is going to be. So this would be plus dot, 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 dot. And I'm just kind of wrapping it around and saying, okay, way, way, way out there, when we get to the nth one is going to have x to the power of n, right, just like we saw there. And then there's going to be this fraction over here. And now it alternates with a -1. So there's something to do with a -1, +1. Okay, so we'll put that on hold. Let's try, we'll put an n there, and then we're going to check and see if our pattern works for that one, and then we might have to come back and add a +1 or something like that. So then in the denominator, looks like it has this match, right? This matches with that. This matches with that. So the power is going to match with the factorial. So there's going to be a n factorial. As we said before, this is twice that. This is twice that. So there's going to be a 2 to the power of 2n, right? That should match that. And then there's this multiplication. And that multiplication is going to be this 1 times 3 times 5 times 6, dot, 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 dot. It's all these odd numbers. And notice that the place we stop is always 1 smaller than that exponent, right? Here we stopped at the first odd number 1 unit below 8. Here we stopped at the odd number that's 1 unit below that one. So here we're going to keep going, and we're not going to stop until we get to the odd number that's 1 below that one, 2n minus 1. Okay? All right, but in order for this to work out way back here, and for this to be our general formula, if I let n equal to 0, I'll get a -1, and that's not what we want. We want this to start at +1, so I can already see that when I create my sum, I want to start at 1, and then I want to come back and make sure that this matches. So if this starts at 1, that would make it negative, and that would reach here for 1. Okay, when n equals to 0, it doesn't quite fit this pattern, because if I have a 0, then I'll have a -1 here. That doesn't quite fit that pattern. So we're going to separate this and just focus on a sum that expresses this infinite sum from here to infinity. Right? I found the nth one, but then this keeps going on forever. Okay, so let's bring it together in one big happy sum. This is going to be x 1, and then I want to express this whole thing right here. So this is going to be plus, and then it's going to be the sum as n grows from 1 to infinity of and then I'm going to have this -1 component, and I want to raise it to the positive n, right? Because that'll give me the first one as negative, and that's what we wanted. And then when n is 2, that'll give me this term over here. So this is going to be for n equals to 1, it'll give me this term. And when n equals to 2, it'll give me this term, hopefully. We're going to guess and check our way through this and make sure we get it. Okay, in the denominator, we're going to have factorials. 1 factorial, 2 factorial, 3 factorial. Okay, so this is going to be n factorial. And then 2 to the power of 2n. Right, so it's going to be matching with this. And then we have this multiplication of 1 times 3 times 5 times 7, right? It only does, it's a multiplication of all the odd numbers. And when do you stop? Well, we keep going. We don't stop until we get to 1 less than this one, 2n minus 1. Right? So it's this really long string of odd numbers being multiplied, and you start at 1, 3, 5, 7, dot, 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 and you don't stop until you get to 1 less than that one. Okay? And then that whole thing, is multiplied by x to the power of n. Okay, there we go. That looks pretty good. Okay, so now we're gonna redistribute this into there and this into there, and we'll get that this is going to be equal to x squared over root 2 plus x squared over root 2 times all of this, and goes from 0, goes from 1 to infinity of this crazy thing, -1 to the nth power, and then this multiplication, 2n minus 1, all over n factorial 2 to the 2n times x to the n. Good. All right, and next we combine some like terms. So remember that root 2, another way to write root 2 is to say, well, we'll cross it off. Another way to write root 2 is 2 to the 1/2 power. So we can bring that in here and add it with that exponent. So we'll get that our final result is going to be that the original equation we were looking for, which was x squared all over got it already. X squared all over 2 plus x. That was the original function we were working with. That is equivalent to this. That's going to be equal to x squared over root 2 plus, and then tucking that into there, we'll end up with a giant sum. This goes from 1 to infinity, and we'll have a -1 to the power of n. And then we have this countdown, 3, 1, 3, 5, 7, dot, 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 all the way, all the odd numbers until we get to 2n minus 1. That's when we know how to stop. And then all of that goes over, there's this n factorial. And now I'm going to do 2 to the 2n times 2 to the 1/2, which is that square root. It's brought into there. And then there's this x to the nth, but then there's also this x squared times x squared. Okay, so now we're ready for the final answer. X squared all over root 2 plus x is equal to x squared over root 2 plus the sum from 1 to infinity of -1 to the nth power, 1 plus 3, not plus, excuse me, 1 times 3 1 times 3 times 5 times dot 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 all the way out to 2n minus 1, right? All of that gets divided by n factorial 2 to the 2n plus 1/2, right? So if we combine these two exponents, we get 2 to the n plus 1/2. Let me fix that a little bit, it looks messy. So combining these two, we get a plus 1/2 times x to the n plus 2. And so as we had stated above, this is going to be true as long as, coming way, way up here, as long as this is true, right? Way, way up here, we got that it was true as long as this was true. So x has to be a member of the set between -2 and 2. So it's valid for those values of x. So this is valid, it's true for x being an element of, a member of, the set between -2 and 2. We can also say that r equals to 2, and it's centered at 0. Or we can also write it as above there, x has to be greater than 2, less than 2. So as long as we choose a value of x that's in this range, then this equality will hold. Okay, so that brings us to the table of common Taylor functions. So let's look at that in your book. Okay, so here it is, page 768. Some of these will look familiar. That's what we've been working on. So we worked out e to the x, for example, and sine and cosine, for example. We just finished working on this one. So we worked it out. We found the Taylor, the Maclaurin series expansion, right, centered at 0. So the Maclaurin series expansions. And then in this very last example, we saw that we can manipulate things just a little bit to make it fit, and then we can find a new Maclaurin series expansion based on some of these really common patterns. Okay, so let's do another example. Let's look at your homework. Let's see what we got. So we did something like that one. We did number 42 right now. For example, if we did number 36, use the Maclaurin series table 1 to obtain the Maclaurin series for the given function. Okay, so then this is very similar to our sine one. Right? So we just go over to our table and look for the one that has sine. Here's the Maclaurin series expansion for sine. So the one we're working with in that problem is very similar, just a little off. So we're going to just adjust things, do a proper substitution, and then try and fix it up a little bit, and we'll get to the one we're looking for. Okay, so let's do number 36. Okay, so notice that in the prior homework problems up here, when you were doing these, the way to solve these, you need to start taking derivatives, right? We need to use our power series expansion of a Taylor. And so you need to start taking derivatives and then plug in x equal to a equal to this value and find them that way. Whereas here, you get to use the table. It says use the table so you can use a pattern that's already been established. So we want to use the pattern for sine because it has something to do with sine. It's just that we have a different value, different argument to the sine function. So we come up here to our table. So here's our table. We want to use this guy. So we know that sine is the one that has odd powers, -1, odd powers, okay? So, okay, something to do with this, and the radius of convergence is infinity. So this is for x being a member of negative infinity to positive infinity. Okay, so we want to apply that. All right, well, in our case, the argument is just a little bit different. So we can say that this is going to be almost the same as that, except we just have to tweak it a little bit. We have negative 1 to the nth power, and then we have something to the power of 2n plus 1, and then we have a 2n plus 1 factorial, and this is for x being a member of negative infinity to infinity. Okay, well, the thing that goes in here is this. So now we have to plug in a pi x over 4, and then simplify it as best we can. Okay, so this is for pi x over 4. So we simplify it and say that this is going to be n goes from 0 to infinity of negative n to the nth power. I'm going to separate this into pi to the power of 2n plus 1 times x to the power of 2n plus 1, and then divided by, and there is a 4 to the power of 2n plus 1 times a 2n plus 1 factorial. And this is for r equaling infinity, right? All real numbers. This was valid for all real numbers, so this will also be valid for all real numbers. Okay, so it's as easy as that. We don't have to start from scratch and build the whole thing. We get to use a pattern. Okay. Likewise, let's try something else. If we tried okay, so we've done a good amount of problems from there. How about evaluate the indefinite integral as an infinite series? Okay, so how about number 56? Find the integral of arctan of x squared. Okay, well, that's something to do with arctangent. So we can go over to our table. They didn't say start from scratch, so we get to use our table, and there it is. Arctan is the same thing as inverse tangent. So here is the Maclaurin expansion representation of arctangent. It's this one, and it's good on a radius of r equals to 1. So let me copy that over here. So it's going to have something to do with tangent inverse of x equaling to the sum from 0 to infinity of negative 1 to the power of n, and then x to the power of 2n plus 1 divided by 2n plus 1. Good. And this is for r equals 1, radius of convergence equal to 1. Okay, so ours is very similar to that one, except we have an x squared instead of just an x. Right? And in case it's not clear, this is arctan of x. Another form, another notation style is to put this little -1 there. Okay, so we want to say that this integral is equal to the integral of this part, which is going to be this. So this is going to be the sum as n goes from 0 to infinity of negative 1 to the nth power divided by 2n plus 1. And then there's this term here, and it's being raised to the n plus 1. Right? So over here, this is where the x would go. Over here, this is where the x would go from our argument. Our argument was x, and the x would go there. So in our case, the argument is x squared. So that's what goes right in here, x squared. Good. So we keep that dx. So this is arctan squared, right? And this is going to be for the same radius of convergence. So this is for r equals to 1. Good. So now we just have to simplify this a little bit. This is going to be the integral of the sum as n goes from 0 to infinity of -1 to the power of n. And so this is going to be x to the power of 2 times 2n plus 1 all over 2n plus 1 dx. Again, we simplify it. Let's expand this. Let's distribute that 2. And so this becomes the integral of the sum of n goes from 0 to infinity of -1 to the nth power x to the 4n plus 2 all over 2n plus 1 dx. Okay, let's expand this a little bit and see what it is. So I'll go in this direction, say it's the integral of, and I'm going to expand this a little bit. When n equals to 0, I get a positive 1. N equals to 0, I'll get an x squared. So the first term is going to be x squared all over, and we put a 0 in there, and we get a 1, so just 1. And then the next term when n equals to, so this is n equals to 0, is that one. 0 there, 0 there, 0 there. Okay, so next I want to look at n equals to 1. When n equals to 1, we'll have a minus. When we get a 1, we'll end up with 6. So this is x to the power of 6 divided by putting a 1 there. That'll be 3. Okay, so this is the case of n equals to 1. It's right in there. Let's just do one more. Let's see, the next one, it's going to be a positive when n equals to 2. When n equals to 2, we'll get 10 here. X to the 10th power divided by, and putting an n equals to 2, we get a 5 here. Right, so here's the case where n equals to 2, right in there. And now I think the pattern is pretty easy. It looks like it's growing by the exponents here are growing by 4s, multiples of 4s. And looks like the denominator, we have odd values. So this is minus x to the 14th power divided by 7 would be my next one, right? That's what happens when n equals to 3. N equals to 3. That makes it 14, and then that makes it 7. Good. And then we just continue in this way. Dot, 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 dot. And then all of this, right? That's just that expansion of this. And then there's a dx over here. Okay, well, we know, coming down here now, we can integrate one at a time. And when we integrate, the way we do it is we add an exponent. So we end up having a 3. And then we got to divide by that. And then this term stays the same. So now this, let's bring out the 1/3. And then this becomes x to the 7th over 7 plus 1/5. And this becomes 10 x to the 11th over 11 minus 1/7 x to the 15 over 15, right? So each time we just add one term plus dot, 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 dot. And we know that every time we do one of these integrals, there's a plus a constant, and then we can just combine all those constants and then have a big plus c at the end. But it looks a little messy to have this go out that way and then a plus c. So it's kind of customary to stick it out in the front and say it's c plus all of that, where c represents the constant we get from all of those. Good? Okay, so then let's try and find a pattern here. This is c plus, okay, well, we could just work with this guy over here. So whether you do it this way, we expand it all out and do it individually, Or you work over here and you see what you do. You need to integrate this. So this will be equal to the integral. We'll come back and confirm the value of n in a second. N starting from somewhere. Let's make sure oops, sorry. We need, okay, so we're going to start off with our c, since we know there's going to be some constant, plus, and then there's this integral. And we know we have a -1 alternating. That's not going to change once we take the integral, right? So we leave that alone. This isn't going to change either, so we leave that alone. We know the way we integrate is we add 1 to this, and then at the same time we divide it by that same exponent, right? So all we did was introduce this +1 here, and then divide by that 3, +1, and then divide by that value. So this is going to be this, x to the power of 4n plus 3. Well, okay, let me rewrite that. How about to the 2n and then +1, right? So I'm adding 1 there, which of course is going to give me the 3. And then I'm dividing by, I'm going to leave this one alone, so that's going to be 2n plus 1. And then I got to introduce this new term, which is going to be 4n plus 2 plus 1. Let's simplify it and confirm that it fits that pattern over there. So it's going to be c plus, and then this runs from 0 to infinity. Let's check to make sure that that pattern works. We didn't lose any terms, so we should keep the same index starting at 0, right? There weren't any terms that fell out of the pattern and turned into a 0. So that should stay the same. So let's put it in there and then we'll check. So this becomes x to the power of 4n plus 3 divided by 2n plus 1 times 4n plus 3. Right? So let's confirm that it works out. So if I was going to expand this, hopefully I get exactly that. Well, the constant is there. And let's see, when n equals to 0, I get a positive. That's a positive. And then 0, I should get x to the third power. That's that one. 0, I should get a 1. And then 0, I should get a 3. So yeah, this guy right here is the case for this guy as n equals to 0. Now let's confirm that this is the term I get when n equals to 1 from this one. When n equals to 1, we'll get a negative. That's true. When n equals to 1, we get a 7, x to the power of 7. When n equals to 1, we get a 3 times 3. And then when n equals to 1, we get a 7 there. Yeah, so this is this thing when n equals to 1. Okay, so it does match. C plus x to the third over 3 minus 1/3 x to the 7th over 7 plus ... the rest of them. Good. So this is our answer. And this is valid for the same R value, the same radius of convergence as the general form that we used. So we used this one. Let's zoom out and take a look at the big picture here. So this is the general form that we use for tangent inverse. And it was good for R equal to 1. So this is also going to be for R equal to 1. And this is centered at 0. How do we know? Because we have x minus 0 to the power of something, right? If we go back to our power function, our general power function descriptions, we have this, x minus a to the power of n, and it goes from 0 to infinity. So this right here is what lets me know where it's centered. And so I don't have a plus or minus constant x to a power. I have, you can insert this as 0. So it's centered at 0. And so the interval of convergence is going to be centered at 0. Okay, so the radius of convergence is 1. So the radius of convergence for that one is going to be the same thing. All right, let's see if we can do one more. Let's see. For these guys, just use the expansions, use your table to replace the functions, and you'll get some very long fractions. Make sure you're very careful about how you substitute them and expand them, and our goal is for a bunch of stuff to cancel and reduce, and then keep in mind the limit that we're working with. Okay, I think those should be okay, I think. How about one of these guys? And then that should be everything you need for the homework. How about number 78? 1 minus ln2 plus ln2 squared over 2 squared minus ln2 to the third over 3. Okay, so find the sum of this series. Number 78. So we have 1 minus ln of 2 plus, and then we have ln of 2 squared all over 2 factorial minus parentheses ln of 2 to the third power all over 3 factorial plus ln of 2 to the power of 4 over 4 factorial, right? So taking some leeway here. Looks like the pattern is established. Okay, so we want to find the sum of this series. How do we find the sum of this series as it keeps going? Dot, 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 forever. Okay, the key here is going to be to take advantage of those, of that table that has the standard ones, right? So make sure you have this handy when you're doing your homework. This guy, all right? So we're looking for something that looks like it, something that's similar, fits the same general pattern, except maybe something that we can replace the input of the argument of the function with, right? So replace the x with a new little function or something, right? Something to substitute it with. So as I look at this, okay, which one does it look like, or does it come close to? It doesn't have anything to do with this one, because this one doesn't have anything to do with a factorial, right? It's definitely not this one, because this one only has the odd factorials, and this one has all the factorials. Can't be this one, because this one has all the even factorials, right? So it's not sine, it's not cosine, I have all the factorials. It's not tan inverse, because I need factorials, and tan inverse doesn't have factorials. It's not ln, right? No, it's not ln. And it's definitely not the binomial, because the binomial is very unique. It's got this weird multiplication of the k minus 1, right? So it's got this k choose n term to it. So it's not that one, not that one, not that one, not that one, not that one. That leaves me just this one as a possible candidate. So we have to tweak it and change it a little bit. So it's got to be something to do with this one. So let me copy it down. So I suspect it has something to do with e to the x, which I know is equal to the sum as n goes from 0 to infinity of x to the nth power all over n factorial, which then, if we expand it out, turns into 1 plus x over 1 factorial plus x squared over 2 factorial plus x to the third power over 3 factorial, right? Plus dot, dot, dot. And this is good for r equals to infinity, right? So the radius of convergence is infinity, r equals to infinity. Okay, so armed with that, let's manipulate this as best we can to make it fit that. Well, this is easy. We can always just stick a over 1 factorial, and that takes care of that. And we started off with a 1. That looks good. And the only other thing that's a little bit different is this minus, right? So if we let kind of tuck it in here, so let's rewrite this a little bit. If we rewrite it as this plus and then negative ln of 2, sort of up in the numerator, over 1 factorial, plus and then negative ln of 2 squared. The squared is going to make that a positive anyway, all over 2 factorial, plus, and now we'll have negative ln of 2 raised to the 3rd power over 3 factorial, plus negative ln of 2 raised to the 4th power all over 4 factorial, plus dot, 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 dot. Now it looks exactly like that one, right? Where instead of having an x, I have a minus ln2. My minus ln2 is my x, right? There's something squared right there. That's this guy, x squared, minus ln2, minus ln2. That's all these x values. Okay, so now that it fits that form, I know that this then must be equal to this guy with the x replaced by minus ln2. So this is going to be equal to the sum as n goes from 0 to infinity of something to the power of n over n factorial, and that something is this minus ln of 2. Okay, so that's this guy. Okay, well, kind of working my way backwards here. I kind of started by making it fit this, and like, okay, well, that means that it can be written this way. So this is the Maclaurin series that this can be collapsed into being this, and this is for a radius of convergence of infinity. And then we make one more connection that this is in fact equal to that. So now we'll go, okay, well then this whole thing is equal to e to the power of x, where x is this thing, minus ln of 2. Right? This was my x, just like here, here's my x. And so now this thing is just equal to e to the x. Right? I started with this long string of addition here, this infinite sum, and then I was able to rewrite it this way using my pattern here. And now this is equal to e to the power of whatever's in there, which is this. Okay, so now we just have to fix that a little bit. This is equal to e to the negative 1 times ln of 2, which is equal to e to the ln of 2 raised to the negative 1, right? When we have an exponent raised to another exponent, we multiply the exponents. So I'm just undoing that, reversing that process. And now this is just going to be a 2. E to the ln of 2 is just 2 raised to the negative 1. And so 2 to the negative 1 is equal to a half. So that's our answer. This infinite sum of all of these values, all of this will add up to a half. That's what we get. Okay, so hopefully we've covered enough material to be able to get you through your homework. But if you have any questions on anything, as usual, please let me know. I'll be available all day tomorrow and the next day and the next day. So let me know, send me an email, and we can set up a Zoom meeting to go over any questions you might have. Okay, good luck.